Hello everyone. In today's general interest seminar, we'll talk about the new developments in OpenMP. So this seminar is not to talk about how to implement OpenMP, but an update for what's available in OpenMP up to date. My name is Jamie Hu, and I'm a Sharcnet HPC consultant based at the University of Waterloo. OpenMP is an application programming interface for writing multi-threaded applications. It consists of a set of compiler directives, library routines, and an environment variable for parallel application programming. So the approach simplifies writing multiple threaded program in Fortran, C, and C++. So we all say OpenMP is easy to use because it provides capability to incrementally parallelize a serial program. Unlike the MPI message passing library, which typically require an all or nothing approach. And also OpenMP it standardizes the established SMP practice. And the current versions support vectorization and heterogeneous device program. So we talk about the past and also the current and then the future development in OpenMP. So if we give a brief history, so OpenMP has over 20 years history. It's actually managed and proposed by a consortium named OpenMP Architecture Review Board. It's jointly defined by a group of major computer hardware and software vendors. Its first API specification that's OpenMP for Fortran 1.0. That was released in 1997. The following year, they released the version for C, C++ standard. It actually took some time, and the first combined C, C++ Fortran version, the 2.5, that was released in 2005. So up to that point, OpenMP primarily specified ways to parallelize highly regular loops as they occur in matrix-oriented numerical programming, where the number of iterations of the loop is known at entry time. Certainly, only parallelized loop was recognized as a limitation, and then various task parallel extensions were added to the implementations. So the concept of tasks and the task constructor were proposed in version 3, and they were largely improved in the later versions of 4 and 4.5. So the present version, well, we say maybe is OpenMP 4.5 because the major compiler support up to OpenMP 4.5 at this point. So in 4.5 and 4.0 and 4.5, many new features has been added, such as support for accelerators and the thread affinity, and lots of task extensions. And also, they have SIMD support, and also the support for the latest Fortran and the C++ versions. So we'll try to talk about some of the main features today. So the latest version is actually OpenMP 5.0. That was released at the end of last year. However, the compiler companies have to catch up with the implementations. and hopefully later this year or maybe early next year, we can see the new compiler versions and some of the new OpenMP 5 version will be implemented. So OpenMP is implemented on top of a serial code. So the backbone of program model is a fork jump models. So programs execute in serial mode until they encounter a parallel directive. So it's always in a way, so the code will run in a serial parallel fashion until the end of the code. So the fork is the master thread create a team of parallel threads. So the statements in the program that are included in the parallelizing constructor are then executed in parallel among the various team threads. And when the team thread completes the statement in a parallelizing constructor, they synchronize and terminate. Then leave only the master thread to run as sequential. So that's the basic as P thread or type of threading code programming models. So in the past, the main part of OpenMP is the Worksharing constructor. So there are three of them. The one is for the dual or for parallel dual, parallel for. So that's the main thing, and to parallel loop, the shared iterations of a loop across the team. So this also represents a type of data parallelism. It has another constructor called sections. The section is actually breaks work into separate discrete sections. So each section is executed by a thread. So the combined is actually run in a parallel way. And this sometimes may be called a functional parallelism. It actually has a third one called a single. A single means something like a master thread. It serializes a section of code. So in this case, it's majorly because the data dependency or somehow the code cannot run in parallel. So it's just let one thread to run. So for loop parallelism, so we all know it's just straightforward. So if we have a simple sequential code, is a for loop here, for example, so we can use as simple as just a parallel directive. So let's basically open a team of threads. And we know we can always call the library function. We can get the thread ID and the number of threads in the team. And we can manually distribute or divide the loop to different threads. Certainly, that's not the best way to go. So then the Worksharing constructor like the for, parallel for, and will do the work automatically for you. So without any change to the loop itself, it's basically you just have a parallel for added on top of the loop, and then the loop will run in parallel by the number of threads you set up at the beginning of your job. So it's simple, and the traditional OpenMP code only use a few OpenMP related lines. So here we list maybe up to 10 or maybe just around 10, something in that range. So any OpenMP code, so we always started with parallel, because that's the key concept. Is actually parallelizing. It opens a team of threads. And then in a parallel OpenMP code, you always need to get the thread ID and the total thread in the team. So and you know how many active threads are running for your code. And if you want to do a performance measure time thing, you can call OpenMP underscore get the world times. And sometimes you may need to use a barrier, you need to critical for synchronization. And most of the time, maybe you don't need it. And the for loop Worksharing is the big thing. And it has reductions, it has some schedule for to deal with how the Worksharing is actually in runtime. And certainly there are some data management, so how to define the data, and the low weight is basically disable implicit barrier. So that's basically the thing when we say a basic introduction to OpenMP. We only cover that many. So now not all program has a simple loop, and in that case, so the past OpenMP cannot deal with that situations. So list here is a program to traverse a linked list. Or linked list, is the loop will be a while loop. In while loop's case, OpenMP, because it can only parallelize the loops in a basic standard form with loop count known at compiler time. So how to deal with this type of situation? The other situation is, say your code does not have loop at all. So this is a typical or simple example. It's for Fibonacci number. So it's a reverse code. There's no loop at all. So how to deal with this type of situation? It comes with the tasks. So the tasks are independent units of work. So tasks are composed of code to execute and task to compute with. So if we think about a sequential code, it's basically it's a task, task, task. So in that case, in concept, we can say run it in parallel, and let one thread pick up one task, and the other thread pick up another task, something like that. Certainly, the tasks are not even run. Some may run finished in a shorter time. So the thread will be basically assigned to perform the work of each task. The thread that encounter the task constructor can execute the task immediately. The threads may defer execution until later. So in OpenMP, it comes with the task constructor. The task constructor, in terms of form, is quite simple. So the syntax will be programmer OpenMP task. And then it comes with there is a task wait constructor as well. The task constructor is going to create a new task and create a task, and the task will be added to task queue. So available threads pick up and next task from the queue to execute. And then task wait will act like a barrier. So it will wait until all shared tasks has finished. So with this task constructor, OpenMP can be used to support irregular program like now it can deal with the while loops or loops whose iteration limit are not known at compiler time. And then OpenMP can use it for recursive algorithms. So something like that. And then it's basically a broader the use of it. So task constructor was proposed is actually in version 3. And in version 3 and version 3.1, and it's actually largely enhanced in OpenMP 4. So OpenMP 4 and OpenMP 4.5 is considered significantly modernized the OpenMP. And then there is a lot of new features to add to it. The major additions include there's SIMD constructor, the single instruction multiple data. And then there's a lot of task-related constructors, like task group, task dependencies, and task loop. And also it can deal with some data conflict, like listed loops that have due across. And then the big thing in OpenMP 4 and OpenMP 4.5 is they added a target device construct. That is actually support to the accelerators. So the target device constructor was first introduced in 4.0 and then was enhanced in OpenMP 4.5. So if we list some of the features here, certainly just pick up some main things. If we put them together, so list here are some major additions in OpenMP 4.0. So the red color here listed is the three things we'll touch with it. The others, there's lots of them. We cannot cover them. So 4.0, they added task groups and task dependencies. And the first time it added SIMD and the device constructors. There are lots of more. You can check it out on openmp.org. And the 4.5, it focused on device support. So it used unstructured data mapping, and it also defined the scanner variables are first private by default, and also they have clause to support device pointers and device runtime routines, like the mapping, allocation, and lots of them. And in addition, there are many clarifications and minor enhancement for what proposed in 4.0, like the SIMD extensions, like lots of schedule things, and the support for the new C++, and the Fortran versions. And it provided a new constructor called a task loop. And then when you do loop, you can actually run it as tasks instead of the traditional the for loop, something like that. It has a task property, and it has more to support for the data racing issues in nested loop, something like that. So if we now talk about, say, OpenMP parallel programming, certainly the Folk-John model still is the model, and certainly it still is a directive-based program model. But we can see, well, it's a multiple-level parallelism supported. It supported CPUs and threads, SIMD, and also the device, different device. So now it's basically largely is task-based. So that's so-called a modern approach to parallelism. It certainly is a high-level access. And then now, people actually, many applications take both approach, the hybrid MPI and the OpenMP approach. And because OpenMP, well, has the advantage to share memory on one node, and the node now has many CPUs. And OpenMP now, by definition, you can run on GPUs or even other accelerator like original Intel Xeon Pi or something like that. So in OpenMP 4.5, the task is considered to be complete. So in terms of the constructor, they have task, and they have task group, and task loop, or task yield. And the clause itself can take different data environments. And it could be if condition, it could be, and you can specify and private or share it and those type of data environment. It currently have a dependency of a priority, and some other mergeable and the final, something like that. So it's a useful tool in OpenMP and for you to apply OpenMP to a wide range of programs. So here, just for fun, list the applications, for example, and the code to calculate Fibonacci number. And if we use task constructor, and OpenMP will work. And the main code is basically your open team of thread, and the master thread will calculate the Fibonacci number, give it a number. And it's actually because the number will be the sum of the previous two numbers. And when you call the function here, well, by definition, x, y, are local to the threads, and you need to know each other, so you specify defined period, and you have to use the task wait and to make sure the job has been done, and then you add them together. So this is just a super easy, super basic example. Certainly you can implement it in different ways. And for list, there's some similar things. So for list, and you have the parallels. You can use a single master to create a team of to generate tasks. And the task each thread is actually pick up a task, and one by one until the end of the task. So that's the way basically task can use it to, well, the while loop can use it to some code, recursive code without loop. Okay. And then task loop, that was proposed in OpenMP 4.5. Say it's basically we have a basic loop structure and use a parallel for loop. Good. And then if we want to do it, use a task constructor, you can still do it as long as you define the task size, and then you can basically run it in a different way. So task size, so each task include how big of a part of your array in that loop. And then you can simply use the task constructor to do it. It will work for you, but by that is basically likes you manually to do something. And certainly for in complicated case, or it's easily may be tricky or may have errors. The task loop constructor is basically you define a basic size, just one line on top of your loop. So this is similar in terms of the syntax. It's similar for the parallel for. There's nothing to change about your loop index. You simply just have one OpenMP4 there. Replaced here is task loop. So let's task loop seems to be interesting and useful tool. And then let's say as starting OpenMP 4.0, the code doacross constructor. It's not a constructor, it's a situation. So in this case, it's basically help with cross-iteration dependencies. In many cases, we have listed loop, and then the second loop and have dependency with the index in the first loop. And traditionally, or you just do one loop. You cannot do both. And then in OpenMP, they have ordered construct. They have collapse construct. So this piece of code is not a real code. It's just a demo for two loops, and then you have a dependency of like 2, and then somehow you can use order 2 or collapse 2, and then you basically you can let it run in parallel ways in OpenMP. So the detailed examples maybe you can find some places, and also you can find on openmp.org. Vectorizations. So vectorizations is an unknown in-core way of exploring data level parallelism in programs by applying the same operation to multiple data items in parallel. So we know some compiler, they will do vectorizations during the compiler time. So like Intel and maybe some other compilers has it at all. It's largely apply commonly to array operations in loops. OpenMP comes with this idea with a constructor called SIMD. So it's a single instructor applies the same operation to multiple data concurrently. And the vectorization basically processes multiple elements of an array at the same time. So the syntax is also simple as SIMD, program OMP SIMD, some clause, and then is a for loop. So here is a basic example to explain how you're supposed to work. So for example, you have it's an array as a loop list, is to cut loop into chunks, and then that fit in a SIMD vector registers. So in this case, we just talk about the SIMD is vectorizes only. It's not run on multiple threads. So the same concept is working for a Worksharing constructor. You have them combined together. So basically you have an array. So the first thing is a distribute array among a team of threads. So each thread will get its work to do. And then SIMD is furtherly vectorize it. Something like that. So this will work. And for example, you have a loop structure, initializations, and you do some calculations. And they use SIMP and the loop. You can use SIMP to work that way, and use a dealer for SIMD for the loop to work. So I show the simple demo here because this actually works, where I didn't care about the performance, but it works. That means compiler has this ability implemented already. Okay. So up to OpenMP 4.5, so we want to parallel loop. We have three ways, three approaches. So the traditional way is the Worksharing model. So it's OpenMP parallel 4, but in Fortune's case, parallel 2. And you can do distribute the workload is like the SIMD, the 4 SIMD. They will also parallelize your loop. And then the third way is actually use a task loop, or you parallelize the loop and divide a chunk of the loop as a task. Well, different implementation may have different performance, or let's say the other thing. Okay. So the other big thing for OpenMP is for accelerators and the so-called host device model. So the idea, I think, is quite straightforward. It's a host-centric. The execution of an OpenMP program starts on the host device. The host device we talk about the thread, so CPU, and it may offload the target regions to target device, for example, the GPU. So in principle, a target region also begins as a single thread executions. So when a target constructor is encountered, the target region is executed by the implicit device thread, and the encoding thread task wait at the constructor until the execution of the region complete. So if a task device is not present, or not supported, or not available, the target region executed by the host device. If a constructor creates a data environment, the data environment is created at the time the constructor is encountered. So that's basically still the normal ways in following the traditional ways in OpenMP. So when OpenMP program begins, each device has an initial device data environment, and you can define it. And the directive accept data mapping attribute clause determine how an original variable is mapped to a corresponding variable in a device data environment. So there's some ways to do it. So the original variable on the host, the corresponding variable on the device, the corresponding variable in the device data environment may share storage with the original environment. So that's the concept, and some basic constructor was proposed in OpenMP 4, and the target constructors takes the similar syntax. So it's basically the name is target, and then target can define what type of device, and then the mapping is the data type, and it can have some other like if expressions or some others. And then there are more afterwards. They have target data constructor, a target update, and they have a distribute, and the clear target, and the teams. The teams create a link of threaded team where the master thread of each team execute the region associated with. You can get the number of teams and number of threads, and you can actually set up the size of it. So they provide multiple ways to control it. So here is basically the show and the structure of a piece of code try to use the target device constructor. So the host itself is basically define what type of device to use, and the map and the allocate, say like if it's a index or array the size, and the map the input and from the results or something like that. And then it start a team of it's basically start the device, and then you loop this type of calculations is basically done on the device. And once it's done on the device, or the host is basically they do update, and sometimes maybe input array on the host or get the partial results, something like that. And then it update the device, and then let the device to continue the work. You may have more other controls and in the new definitions, and it just basically show this type of OpenMP structure can apply to the accelerators. Now we have OpenMP 5.0, the latest versions. There are lots of the specifications available on the website www.openmp.org. And on the front page, it's come with these articles. It's called OpenMP 5.0. It's a major leap forward. It's full support for accelerators and the neutral APIs. So the list of fields, I simply copied it here. So the first one is full support for accelerator devices. So OpenMP now has a full support for accelerator devices, including mechanisms to require unified shared memory between the host system and the core processor devices, the ability to use device-specific function implementations, data control of implicit data mappings, and the ability to override the device offload at runtime. In addition, it supports reverse offload, implicit function generation, and the ability to copy object-oriented data structure easily. Sounds very good. And then it improved debugging and performance analysis. Two new tool interfaces enable the development of third-party tools to support intuitive debugging and deep performance analysis. And then it support for latest versions of C, C++, and Fortran. OpenMP now support important features of Fortran 2008, C11, and C++17. And support for fully descriptive loop construct. Loop construct lets the compiler optimize the loop while not focus on any specific implementations. This construct allows the compiler more freedom to choose a good implementation for specific topic than do other OpenMP directives. Multi-level memory system and memory allocation mechanisms are available that place data in different kinds of memories, such as a high bandwidth memory. New OpenMP features also make it easy to deal with the numerous of modern HPC systems. Enhanced portability. The declare variant directive and the new meta directive allow programmer to improve performance, portability, adapting OpenMP programs and user code at compile time. Or because the compiler does not support this new release at the moment, so we do have some online resources I found a few and briefly covered here. So this is some of the new main features. There's a bunch of them. Look at the brand new task reduction directive constructor. And it has lots of memory allocators, and you can use unified shared memory. As a loop constructor to maximize automatically the best way to for the compiler during compile time, and they have lots of new features. The task reduction is newly proposed in OpenMP 5.0. So it looks like where you have parallel and you can have parallel group, task group. You can do the task reduction as the traditional way, reduction to arbitrary numbers, like you do the sum, you do the maximum. That was available in the past OpenMP, and now they extend the list to the arbitrary task graphs. And it extends the existing task and task group constructor, and it also works with the task loop constructor. So that's what a piece of code someone posted online. And then another big thing is the memory allocator. So the memory allocator will allow you to define the memory, and particularly when you use the accelerators. So the user has a default, and you can define, you can switch it. So like the high bandwidth memory, or like the usage with the low latency memory or something like that. So until we actually do some real implementation, we have a better understanding and how do they work. So this is a piece of example taken online to say, well, they can define the allocator. You can define allocator, and then when you allocate your data, you can actually, this is your defined. If you don't, it always has a default for you. And you can define your data type and based on the memory allocators. And then you can actually use them and to how to map it, the data, how to manage with the memory things. And then this sounds is good. It requires unified shared memory. So if this is the case, or maybe don't be too worried too much about the memory allocators. It's actually single address space over CPU and GPU memories. Data migrate between CPU and GPU memory transparently to the application. No need to explicitly copy it. Sounds encouraging. So you have to OpenMP. If you require unified memory, shared memory, and then you simply just use talk, use a team, distribute your work, the parallel work. Done. Okay, so I think that's pretty much an update. Certainly, I just picked up a few major things. The specifications has hundreds of pages, several hundreds of pages. We know OpenMP, it doesn't matter how you implement it. It depends on the compiler to support it. So to have a knowledge about the compiler is a requirement. So nowadays, so far on our computer candidate systems, we have these two types of compilers for sure. So one is the GNU, the GCC, and the G-Fortran. They are open, free, and open source, and we update it when a new version is available. For this set of compiler, from GCC 6.1, OpenMP 4.5 is fully supported for C++. And then Fortran is supported afterwards. If we use the GCC or G-Fortran compiler, and then the options to enable OpenMP is -f OpenMP. If you compile with -f OpenMP, your code is OpenMP code. If you don't, well, the compiler will deal with all the OpenMP syntax as a command line. Your code will still run as a sequential code. Intel compiler, OpenMP 4.5 supported in versions 19.0, 18.0, or even some of them in 17.0. Those compilers are available on computer candidate systems. When you use Intel compiler to compile OpenMP code, you need to add -q OpenMP in your compiler command. If we want to know the full state, many other compilers they support OpenMP. Certainly some are in different ways. You can go to openmp.org. On the resources, there's OpenMP compiler course. They have a full list of what type of compiler, which versions support what type of OpenMP versions. And the OpenMP 5.0 GCC and GNU compiler is said it will start to implement OpenMP 5.0 in the latest version 9, and it said well only part of it can be implemented. The more will come in the future. Intel and I think it will come with upcoming versions, but I didn't find the statement what's the timeline for it. Well, it will be there, and we can use it at some point. So the main resource for OpenMP is the www.openmp.org. They have all kinds of resources there, and certainly we can find some online resources. Some of my slides I took from the online resources as well. And if you want to actually implement OpenMP to your code, I would suggest you to check for the examples provided by openmp.org. There are examples for 4.5. There are examples for 4.0. Examples for 5.0 is coming maybe sometime. It's not there. Okay, that's all for today. Thank you.